Okay, this is the report for machine learning DS675. I'm Kevin Kaplan, and I worked with Travis Virgil on this project. The dataset that we chose was the Animals-10 dataset. This dataset contains 26,179 images of animals, each belonging to one of 10 classes, as you can see here. Here we have the class distribution. You can see that there's a slight class imbalance, with spider and dog being the two highest, and of course elephant being the lowest. So our main learning objective in this project was to classify the images of the Animals-10 dataset. In order to do that, we created convolutional neural networks. Several homemade CNNs were trained and tested. Each one of those were analyzed and altered in an attempt to get a better performing model. From there, we used interpretive methods to help guide our decisions on how to improve those models. We additionally trained and ensembled pre-trained CNNs with our models and used traditional machine learning methods for another comparison. Initially, 14 models were trained. At each iteration, adjustments were made based on the analysis of the model, tuning the hyperparameters and changing the architecture in order to try to get a better model. Here's the architecture of the initial model we started with. There's 3 convolutional layers as well as 2 fully connected layers before the final output layer. The initial results from that first model are pretty good. We can see it as about 75% accuracy, so this is definitely a good starting point, but we're going to look for areas we can improve in. To do that, we'll first look at the confusion matrix. One thing to note right off the bat is that it's clearly over-predicting and over-classifying that largest class, dog, and a bit for spider as well. We can see that there's a good amount of confusion between the insect classes, spider and butterfly, and there's a lot of confusion as well between some of the mammal classes, notably dog and cat, cow and dog, and a bunch of others. So one of the first things we tried to improve our model was to use class weights to help mitigate that class imbalance. The confusion matrix on the left is without, and the one on the right is with class weights. So right away, if we look at the one on the right, we can see that it is not over-predicting dog nearly as much. However, it's now just misclassifying a lot of those dog images. On top of that, the next highest class after dog was spider, and now it seems to have picked up a bit more of an over-prediction for that class as well. This is definitely something that can be fine-tuned and worked with more, but for the most part, we didn't use it too much more after that. In addition to the class weights, a lot of other modifications were tried and tested. Some of those included different activations, different regularization techniques like L1 and L2 regularization, as well as dropout layers. All different combinations of filters and strides were tested as well. Different orientations of layers, adding more dense layers, removing them, adding more convolutional layers. But at a certain point, the cost of doing this is pretty high because it takes a long time to train these models. So we got to a point where we wanted to try to make a more informed decision on what to do next than just the information we had available. And to do that, we would look into the interpretability methods, which we'll talk about in a minute. So here are the results from all of the different iterations of the model we tried. You can see we got some good results, some not as good results, and a whole bunch in the middle. Out of these models, it looks like the best performing one is model 11. So we will continue our experimentation with that model. Here's the confusion matrix for that model, model 11. We can see from this that there's one really big standout confusion here, the confusion between dog and cat. And so that is what we're going to look into the most with these interpretability methods. Interpretability methods are intended to give us a deeper understanding of how the model is making decisions. Here you'll see it helps us visualize kind of what the network is seeing, and we hope to use that information to get further insights about how these images are being classified and to use that information to help us make informed decisions on improving the model. The main interpretability method class that we focus on is called gradient-based methods, and we specifically look at saliency maps, GradCam, path-integrated gradients, and GradCam++. Saliency maps highlight critical regions of the input and then relies on gradients to determine which pixels impact the model's predictions the most. Here we have an original image, the vanilla saliency map, and the smooth grad saliency map, which is an improvement upon the vanilla ones. We can see from these results what the model is focusing on when it classifies this image. GradCam uses gradients to get neuron importance weights. It then generates activation maps with that information, which we can then visualize and interpret. Here you can see that the model might be picking up some of the features of this dog, but it's really heavily focusing on the hairline of this woman. Next, path-integrated gradients work to calculate feature importance by using the integral of the gradients along paths connecting to a baseline to the input of the image. We can see again that the model is really focusing on irrelevant features here, really picking up on a lot of the stuff in the background. Finally, we have GradCam++, which is an improved version of GradCam. From these images, we can see still that the model is focusing on some irrelevant features in some of these cases, but we do see that it is picking up on some distinguishing features like eyes, nose, and fur of the dogs, but it's still misclassifying it. So we could try to improve this model by helping it identify finer distinctions between the classes through those methods. So we have our main ideas of what we want the model to do, and we can try and address that in a couple of ways. First, we can use more aggressive data augmentation techniques and more of them. Hopefully that will provide the model with more diverse data to learn from and let it focus on some of the more important and generalized features and ideally ignore some of those irrelevant ones that it's been focusing on. And we can also just try to get the model to capture more and more complex features. Of course, with this, we need to be careful not to overfit it, but the first 3 models are trained with that in mind, and you'll see those in a second. And then after, we modified the architecture, taking all of that into account, and by adding additional convolutional layers and increasing the number of neurons in the dense layer. And that had some good results, but it seemed to be overfitting a little bit, so we took out the last dense layer and got the best results from that model. So here we can see the results from those model changes. Model 19 is the first one with the newer architecture, and Model 20 is the final one with the best performance. And just to show you, here's the construction of Model 20. So here's the confusion matrix for the final model. We can see that the model not only in general has improved, but has improved in the areas that we were focusing on as well. The confusion between cat and dog has definitely gone down, and we can see that confusion among certain other classes has gone down as well. There's certainly a lot more that can be done to keep working on this, but this is where we got to. In addition to CNNs, traditional machine learning methods were tested as well for comparison. However, between the time it took for feature extraction, data preparation, and training the models, especially support vector machines, it did not seem like a feasible option compared to CNNs. Both of the models were able to achieve about a 34% accuracy, and while that could definitely be improved, the cost of doing it was definitely not worth it. Now I will turn it over to Travis to talk about his portion of the project. Thank you.
In this section, the focus is on pre-training models and utilizing transfer learning to apply them to the Animal-10 dataset. Two pre-training models used are Exception and VGG16. One of the main reasons for choosing Exception and VGG16 is that they are not commonly used in other Kaggle projects. We wanted to perform transfer learning utilizing something other than what is most commonly used, such as EfficientNet and ResNet. We thought this could lead to some interesting results that have not yet been observed. Exception uses depth-wise convolutions followed by point-wise convolutions, aiming to capture spatial and cross-channel correlations efficiently. This leads to reduction in computational complexity while preserving representational power. So one of the main reasons to choose Exception is because of the low computational cost. Exception is also known for having above average performance for computer vision tasks such as image classification, which is our intended use case. VGG16, on the other hand, has a more straightforward architecture designed to consist of repeated smaller convolution of filters followed by max pooling layers. This model offers stable performance for various data sets and tasks. However, it does have a high computational cost and memory usage due to its deeper architecture. One of the main reasons for choosing VGG16 is that it offers different pre-processing in the use of its image sizes. It requires 224 by 224 instead of 299 and 299 like Exception does. We thought this would offer some variation compared to Exception while still maintaining our desire to use a non-commonly used pre-trained model. Throughout this report, you will see the use of various notable libraries, including TensorFlow, Keras, NumPy, Pandas, and Matplotlib. We use TensorFlow and Keras to do most of the heavy lifting for training, validating, and testing the models, while Pandas and NumPy are used for data preparation and Matplotlib for displaying results. To obtain the dataset, we used two different methods. One was downloading the dataset locally, and the other was using an API key and username to obtain the dataset straight from Kaggle. Next, you'll see a list of class names and their various counts of data points for each class name. This can be seen in the bar chart titled Class Distribution. An interesting note for the class distribution are the amounts of data points and images for each class. You will notice that cane and ragno have significantly more data points than others such as gato and elephant. This may lead to the model favoring cane and ragno over other less common classes. As noted previously, this data set consists of more cane and ragno data than some of the other classes. In order to counteract and reduce the likelihood of overfitting, we performed data augmentation. We utilized some of the Keras properties of random flip, random rotation, and random contrast to randomly flip, rotate, and adjust the contrast of the input image. These augmentations introduce variations to the training data, allowing the model to learn from a more diverse set of examples. By applying these transformations randomly, the model becomes more robust and less sensitive to minor variations in the input images and leads to a better generalization of the model. After importing, preprocessing, and data augmentation, we can finally fit the model to the data. Let's take a look at our first model, completed by exception. You will note that it is highly accurate at 97.6% accuracy, precision, F1 score, and recall. This is not uncommon coming from pre-trained models, as they have been trained over large data sets. What is a bit more interesting is the confusion matrix. You will note that the model performs very well, usually only confusing images for those animals that are similar, such as cows and sheep, cows and horses, butterflies and spiders, etc. Another note is that most of the confusion happens between the dog class and other classes. Some of this may be because the dog class is the most common in the dataset. Looking further, we can see the model loss. During the training process, the model loss decreases exponentially as the model learns the data. In contrast, the validation train set takes some time in order for the loss to decrease. This is a sign that through the first few epochs, the model is having difficulty learning the data, but eventually, around epoch 5, is figuring out the data and the loss function decreases. Next, we can evaluate our VGG16 model. You'll see that it also has a very high accuracy, precision, F1 score, and recall of 95.5%. Not quite as high as exception, but still quite good performance. Looking at the confusion matrix, you'll see that it performs very similarly to the exception model, with it confusing similar animals such as cow, sheep, horses and cows, and butterflies and spiders. You'll also notice that once again, dog gets confused with many other classes, more frequently than the others. This is most likely because dog is one of the most frequent classes within the dataset. Looking next at the model loss, you'll notice that the training data for GG16 has an exponential decrease, while the validation set performs somewhat erratically. This is a signal that VG16 was having some difficulty learning the data. In the future, to smooth out the validation loss, we might adjust the learning curve or implement regularization to help prevent overfitting and smooth the curve. Ensemble learning involves combining multiple individual models to create a stronger and more accurate predictive model. Instead of relying on a single model's predictions, ensemble learning leverages the collective predictions of the models to improve the overall performance of the prediction. We employed two types of ensemble learning: majority voting ensemble and weighted ensemble. For majority voting, we utilized the predictions across the three models and chose a prediction that came up the most times for each image, so 2 out of 3 times in this instance. The results were 95.9% accuracy, precision, F1 score, and recall. This is less than exception, but more than the VGG16 and the homemade CNN on their own. The results are less than exception because the voting weights are equally distributed across the three models for each prediction, and thus exception can be outvoted by VGG16 and the homemade CNN. These results led to the implementation of the weighted ensemble, where we could assign weights to each model. Weighted ensemble learning assigns varying weights to the predictions of different models. The weight in this case are predetermined by us, and therefore we can control which model gets more voting power for the prediction. Because exception had a higher accuracy on its own, we chose to give it more weight while still allowing it to be overridden if both VGG16 and the homemade CNN had the same prediction. The accuracy of the weighted ensemble was still less than exception alone at 97.4%, but it was an improvement of 2% over the majority voting method. Through this project, we were able to achieve our goal of getting greater performance through informed decisions utilizing knowledge from interpretable machine learning methods. In future iterations, it may be interesting to perform a weighted ensemble or majority voting ensemble with multiple iterations of the homemade CNN. It may be worthwhile to see how close in performance the ensemble could get to the exception pre-trained model. It also seems that improving a very highly accurate model, such as exception, is very difficult. However, it may be interesting to combine models that are accurate specifically on images where exception sometimes struggles. For example, we could construct a model that performs exceptionally well on cow and sheep differentiation, or butterfly and spider differentiation, and allow it more weight when those prediction percentages are close between those two classes. Thank you for watching our presentation. We hope you enjoyed it and perhaps you learned a little along the way.